Hello everyone, my name is Olivia Pal.
My name is Oishik Nandi.
And my name is Ankan Saha.
And today we will be presenting a review on the paper titled A 45 nanowatt 10-bit 20 kilo samples per second SAR ADC based on single-capacitor switching scheme in 180 nanometer CMOS, which was published in IEEE Transactions on VLSI systems. Let us first look into the background of this architecture. Why is it even required? The answer lies in the increasing use of biomedical implants in medical science. As technology is progressing, these implants are getting smaller to help integrate in newer and more delicate organs. So, their battery sizes are reducing, but the power consumption of these chips are increasing since we need highly accurate data from the body and heavy processing for the implants to be effective. Also, at the same time, the operations required to install these implants are invasive and require complicated operations. So, we want the lifetime of the implants to be as high as possible to reduce the frequency of battery replacement surgeries. We take the examples of leadless pacemaker and injectable heart monitor, which typically have battery capacity in the range of 0.38 watt hour and 0.45 watt hour respectively. Considering battery lifespan of about 10 years, the average power consumption has to be 4.34 microwatt and 5.14 microwatt respectively. Now, all these implants analyze different body signals such as cardiac rhythm, iron concentration, or blood density and flow rate. All these signals are essentially analog signals translated to electrical domain using different sensors. These analog signals need to be sampled by analog to digital converters or ADCs. For most critical implants, continuous monitoring of these signals is required, and this means that the ADC needs to be on for most of all the time. Our body signals are generally very slow, hence they do not require very fast ADCs such as flash or pipelined ADCs. However, they need to optimize in both power and area, as we already saw from previous slides. We see that conventional SAR ADCs of the same specifications have a power demand of almost 1 microwatt, which is 25% of the entire power budget. If a budget of 5 microwatt is considered, this is due to the high switching power loss in capacitive DSC of SAR ADCs. However, this solution has a power demand of just 45 nanowatt, amounting to less than 1% of the power budget of 5 microwatt. This low ADC power consumption gives us three options for our use case. We can have more power share for the signal processing circuits or reduce the size of the battery required for the same processing and lifetime, or increase the lifetime of the device, keeping the battery the same. Now we will look into how this architecture is different from standard SAR architectures, which will be presented next by Oishik.
So now we first look into standard SAR ADC architecture. The standard SAR ADC architecture consists of a capacitive digital to analog converter, a comparator, and digital logic for the switching of the capacitors and generation of digital output. The capacitors used in the CDAC are binary weighted and go from 2 to the power of 0 C to 2 to the power of n minus 1 C, where C is the unit capacitance. In the sample and hold phase, the capacitors of the CDAC store the input signal information in the form of charge. Then, according to the digital logic, the capacitors are switched and the bits are resolved one after the other. The main disadvantages of this architecture is large size of the capacitors used, which affect the area and also the charge change and the power loss during the MSB switching, and also the large voltage changes from the reference voltage to the ground and vice versa cause a lot of power loss. For the proposed architecture in the paper, a drastic change is performed. The capacitors corresponding to the two most significant bits are removed, resulting in the capacitors only going up to 2 to the power of n minus 3 C. This leads to the reduction in the capacitance array by 75%. Also, for the rest of the bits of the ADC, single capacitor switching is employed, where only one capacitor is switched per bit for conversion to reduce the overall power loss due to capacitive switching in the capacitive DAC or CDAC. To explain the mechanism, we take the example of a 4-bit SAR ADC. Following the proposed architecture, first the sampling stage takes place where the top plates of the CDAC are connected to VCM while the bottom plates are connected to the positive and the negative differential inputs respectively. At the end of the sampling stage, first the top plate switches are opened and then all the bottom plates are switched to VCM. Since all the capacitors are switched together and there is no charge sharing, energy spent here is zero. The most significant bit is now resolved by comparing the comparator inputs, which basically checks whether the differential inputs VIP is greater than VIN or not. Depending on the MSB, the next bit is resolved by checking whether VIP is much greater than VIN or vice versa. This is done by either setting all the bottom plates of either the P side of the CDAC or the N side of the CDAC to the reference voltage or Vref, depending on the MSB as is shown in the slide, and then recording the comparator result. This operation results in an energy loss of 1/4 of C times Vref square, which is clearly shown in the slide. For the rest of the bits, we use single capacitor switching as mentioned before. Depending on the two MSBs, the circuit is in one of the four states A, B, C or D as shown in the figure. In each of the cases, the subsequent bits are resolved by switching the required bottom plates from the reference voltage to the common voltage or from the common voltage to ground. This means that the voltage difference between the switches is always Vref by 2. This is considering that the common mode voltage is Vref by 2 and this is instead of Vref, which was the case for standard SAR ADC architectures. So this means that the new CDAC architecture reduces the switching voltage from Vref to Vref by 2. This new CDAC architecture comes with its own difficulties, which are tackled in unique ways as will be presented by Ankan.
So now we will look into the circuit level implementations and the results, starting with the comparator. The single capacitor switching scheme used by the proposed architecture, although saves power, it results in the fluctuation of the common mode voltage at the comparator terminals by large amounts. This means that normal CMOS comparators that have offsets depending on the input common mode level cannot be used in this case. Due to this reason, the authors have used the time domain comparator here. This is realized by converting the voltage difference from the positive and negative CDAC outputs to a proportional time delay using a voltage controlled delay line or VCDL, which is essentially a cascade of voltage controlled delay elements where each element is a skew controllable inverter. This converts the voltage comparison to checking which delay arrives first, which is a very digital friendly nature and immune to common mode voltage fluctuations. Since the circuit is being implemented in 180 nanometer CMOS technology instead of much smaller technologies like 28 or 65 nanometers, it is difficult to get very small capacitors, which is required here. Since even though we have seen that we have eliminated the capacitors corresponding to the first two bits in the circuit, we still need a very small unit capacitor as the largest capacitor is still 128 times the unit capacitance. Otherwise, switching losses would be high. As a result, the authors, instead of using the capacitors from the PDK, developed custom metal oxide metal capacitors, where capacitors are realized by having oxides as insulators sandwiched between two metal layers. This custom design helps them to achieve a unit capacitance of 1.5 femtofarad, which is very small for 180 nanometer technology. The measured results verify the low power consumption at 20 kilosamples per second. The power consumption is 45 nanowatts with a Walden figure of merit calculated to be just 5.06 femtojoules per conversion step, which is state of the art for 180 nanometer technology. The signal to noise and distortion ratio is 56.4 decibels, hence the effective number of bits is 9.26 bits, which is very close for such low power device. Also, looking at the distribution of power consumption, the effect is clearly noticeable. The capacitive DAC, which generally accounts for the largest fraction of the power consumption, is the lowest fraction here, with it only accounting for 24% of the total power consumption, while the digital logic is responsible for 51% of it. Hence, we can sufficiently say that They have removed the bottleneck from the analog front end of the SAR ADC. In conclusion, we see that this paper shows how we can achieve the design of ultra low power ADC by using just simple 180 nanometer technology. By rethinking the switching algorithm and using time domain processing, the authors created an ADC that fits perfectly within the tight energy budget of biomedical implants. This architecture could extend the life of life saving devices by years. Thank you.